Script. Hey everyone, welcome back. Today we're looking at a Leetcode problem called Count Good Triplets. It sounds a bit mathematical, but don't worry. We'll break it down step by step. The goal is to find specific groups of 3 numbers in a list that follow certain rules. Let's dive in. Dine script. Okay, so here's the official description. Essentially, we're given a list of numbers called arranged by binary. And we're also given 3 other numbers, A, B, and circa. Our job is to find how many combinations of 3 indices, let's call them I, J, and K, exist that satisfy a few conditions. First, the indices must be in increasing order. I comes before J, which comes before K. Second, the absolute difference between the number at I and the number at J must be less than or equal to A. Third, the difference between the number at J and the number at K must be less than or equal to B. And finally, the difference between the number A back at I and the number at K must be less than or equal to circa. Phew. That's a lot of conditions, but we just need to check them all for each triplet. The constraints tell us the list won't be too long, up to 100 numbers. And the numbers themselves aren't huge, up to 1000. Let's look at an example. Script. Alright, let's walk through the first example. The list is 301197, and our difference limits are A equals 7, B equals 2, circa equals 3. We need to find triplets, I, J, K, where I less than J less than K. Let's try the very first possibility. I equals 0, J equals 1, K equals 2. The numbers are 3, 0, and 1. First check. Is the absolute difference between 3 and 0 less than or equal to A, which is 7? Yes, 3 to 0 equals 3, which is less than 7. Good. Second check. Difference between 0 and 1 is 0 to 1 equals 1 less than or equal to B, which is 2. Yes, it is. Good again. Final check. Difference between the first and third numbers, 3 and 1, is 3 to 1 equals 2 less than or equal to C, which is 3. Yes. Since all conditions passed, this triplet, 3, 0, 1, is a good triplet. We increment our count to 1. Now, let's try another one. Say, I equals 0, J equals 2, K equals 4. The numbers are 3, 1, and 9. Check 1. 3 to 1 equals 2, less than equals A, 7. Okay, check 2. 1 to 9 equals 8. Is 8 less than or equal to B, which is 2? Nope, it fails this condition. So we stop checking for this triplet. It's not good. We'd continue this process for all possible I, J, K combinations. The example says there are 4 good ones in total. So what's the most straightforward way to solve this? Well, we could just do exactly what we did in the example. Systematically check every single possible combination of 3 indices I, J, and K that are in increasing order. For each combination we find, we just test if it meets the 3 difference rules, A, B, and C. If it passes all 3, we count it. This involves picking an I, then picking a J after I, then picking a K after J. That sounds like 3 nested loops. This kind of approach usually has a time complexity around big O of n cubed, where n is the number of items in the list. Now sometimes n cubed is way too slow, but let's remember the constraint. N is at most 100. What's 100 cubed? It's 1,000,000. Computers can handle 1,000,000 operations really fast, so this simple n cubed approach might actually be perfectly fine here. Script. Okay, here's the Python code for that direct, brute force approach. It looks pretty much like you'd expect, based on our discussion. We initialize a counter to 0. We get the length of the array. Let's call it n. Then, we start our 3 nested loops. Don't worry if it looks a bit dense right now. We'll break down each part next. The core idea is exactly what we talked about. Pick I, then J after I, then K after J, and check the conditions. Script. Let's start with the outermost loop. This loop is responsible for picking the first index of our potential triplet, the index I. It starts at index 0 and goes up to n-3. Why n-3? Because we need to leave at least 2 spots after I for J and K to exist, right? Remember, we need I less than J, less than K, so I can't go all the way to the end. Script. Alright, inside the I loop we have the second loop. This one picks the middle index, J. Crucially, it starts from I plus 1. This guarantees that J always comes after I. It goes up to n2, because we still need to leave 1 spot after J for K. Now, Notice something clever here. Right after picking j, we immediately check the first condition. Is the absolute difference between the number at I and the number at j less than or equal to a? If this condition fails, there's no point in even looking for a k. This triplet can't possibly be good. So, we only proceed to the inner loop if this first condition passes. It's a small but nice optimization. Script. Okay, so if the check between I and j passed, we finally enter the innermost loop. This loop picks the third index, k. It starts from j plus 1, making sure k always comes after j. It goes all the way to the end of the list, n. Inside this loop, we perform the final two checks. Is the difference between the number at j and the number at k less than or equal to b? And is the difference between the number back at I and the number at k less than or equal to c? If both of these conditions are true, and remember, the first condition between I and j already passed, then we've found a good triplet, so we increment our count. After checking all possible k's for the current I and j, the loops continue until all combinations are exhausted. Finally, the function returns the total count, the call script. So how efficient is this three-loop solution? We measure efficiency using big O notation. For time complexity, since we have three loops nested inside each other, and in the worst case each loop might run roughly n times, where n is the length of the input list arranged by, the time complexity is big O of n cubed. Now n cubed can sound scary, but remember the problem constraints. N is at most 100. 100 cubed is only 1 million. Modern computers can do way more operations than that per second, so ON cubed is perfectly acceptable and will pass the time limits for this problem. What about memory or space complexity? We're only using a few extra variables to keep track of the count and the loop indices, I, j, k. The amount of extra memory we use doesn't really grow as the input list gets bigger, so we say the space complexity is big O of 1 foot or constant space. That's really good. Script. Alright, let's quickly recap. The core task was finding triplets of indices I, j, k in order, such that the numbers at those indices satisfied three different absolute difference constraints involving a, b, and circa. Because the maximum size of the input list was small, n equals 100, the most straightforward solution, using three nested loops to check every single valid combination, was efficient enough. This gives us a big O of n cubed time complexity and big O of 1 foot space complexity. We also saw a tiny optimization by checking the first condition early before entering the innermost loop. Simple, direct, and it works. Script. Hope that breakdown made sense and helped clarify the problem and the solution. If you found this helpful, please hit that like button, consider subscribing for more Leetcode explanations, and feel free to leave a comment if you have any questions or thoughts. And hey, if you're feeling extra generous, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.